Welcome to your first video in modern physics. In this video, we are going to be learning about cloud chambers, bubble chambers, and we're going to review the charge to mass ratio. And we're going to learn why this is important in modern physics. For a quick prelude into bubble chambers and cloud chambers, I have a picture for you to ponder about. The picture on the left is a picture that would be used by park wardens, biologists, or hunters. Whereas the picture on the right is one that is used by physicists. So as you ponder these two pictures, I want you to think, why would physicists want to use the picture on the right, and why would biologists, wardens, and hunters want to use the one on the left? So I want you to think, how is this related to biologists, hunters, and park wardens in the same way that this picture here may be related to physicists? So I want you to pause the video for a bit and think. So now I want you guys to pause the video and read pages 830 to 831. From the information you get on those pages, I want you to make a Venn diagram to compare cloud chambers and bubble chambers. You will have 10 minutes to do this. Be prepared to share your Venn diagram with other classmates in class. So now that we have made and shared Venn diagrams, I want you to think, why will neutral particles not show up in a bubble or cloud chamber? Also, how could you tell if a neutron were involved in a particle collision in a bubble chamber? So I want you to think about what you wrote down in your Venn diagrams. What do we need in a bubble chamber to turn the liquid into a gas? What do we need in a cloud chamber to turn parts of a gas into a liquid? So pause the video and see if you could answer this question. Think very deeply as to why. So now let's review my hand rules. So here we will have two diagrams, and I want to figure out what type of particles are they. Are they positive, negative, or neutral? Well, let's try my first diagram here and look at my hand rule. So right here, remember, if we have an X going in, that's the tip of an arrow, so it's going in the field. So I'm going to rearrange this so it's going in. And if this is going in and we're using our left hand, remember, left hand's for electrons or a negative charge, I look at it, the force is going to be pushing outward from the palm of the hand. My velocity is going the right way, but my force is going outward. That means my curve, in this case, should be going down if it was a negatively charged particle. But it's not. So now let's try my right hand. If I use my right hand, like we said, it's going into the page. So if I put my right hand into the page and my velocity coming out, what's going to end up happening is my force is going to be going upward. And that's what's happening here. My charged particle is curving upward. So that must mean this one here is going to be a positive, because it's the right hand that matches what's happening in this pit diagram. Now let's look at my second one here. Here we have my magnetic field coming out of the page, because we're seeing like the pointed end of the arrow. So let's try once again with my negative charge hand, my left hand. If my left hand, we are going out of the page, so it's coming out towards us, we could say. So if I'm putting my hand out towards us, but let's match the velocity, and we're coming out towards us, then it's going to be going outward this way. So my path should be curved this way, the path of the particle. That's not happening. So now let's try my right hand. So it's coming out towards us. So let's rearrange this. So it's coming out towards us. It's out of the page. My velocity is going that way. It's out of the page. So I'd have to point my hand towards me. And the force is going to be coming inward if we analyze that very closely. So this is following the path properly. So both of these end up being negative charged particles. So now let's look at our first example. Assume that the tracks shown in this figure down here were made by particles moving at a speed of 0.1 times the speed of light through a uniform magnetic field of 30 milliteslas out of the page. The initial radius of each track is 5.7 millimeters. Determine the charge to mass ratio for the particles. Then make a hypothesis about what the particles are. what is unusual about this pair of particles? So first of all, I want to know if these particles are positive or negative. So I'm going to use my hand rules. Now, if we remember, it says right here, the magnetic field is going out of the page. So I'm going to have my fingers pointing out and see which one happens. If I use my left hand, I find, and I have my thumb following the lines, it's curving inward and my hand's pointing inward, so this side here is negative. But my left hand doesn't work for the right side of the picture. In that case there, I have to use my right hand. Because remember, it's coming out of the page, so I'm going to point my fingers out of the page, have my thumb following the line, and see if it's bending towards where my palm is pointing. And in this case here, we know this side here is going to be positive. Now, if we're looking at this, here's a little hint of what we must look at for these calculations. We're looking at a magnetic field and we have a particle bending or turning. And it's the magnetic field that's helping it bend. So in this case, for my hint here, what we want to do is we're going to say the centripetal force must be equal to the magnetic force. In cloud and bubble chambers, we're measuring particles that are really, really small. So it's nearly impossible to find the mass of these particles. Remember how hard it was to find the mass of an electron. It took all the way to milliken to find that. So for these, yes, some of them may be electrons, some may be protons, and so on. But we are also sometimes looking at even tinier particles that we'll learn about later. So to do these here, we're going to be using the charge to mass ratio. So very similar to our calculations done with J.J. Thomson, where we had my magnetic field is equal to my centripetal force. So now I want to rearrange these formulas when I plug them in so I get my charge to mass ratio. So we know the force of my magnetic field is equal to my magnetic field multiplied by my charge multiplied by the velocity, which are all perpendicular to each other, which now is equal to the force, my centripetal force, which is equal to mass times velocity squared divided by my radius. Now we're trying to isolate for my charge over mass ratio. So I'm going to first put my mass on the side, so I have charge over mass. Okay, now I'm going to continue isolating, so I'm going to get my charge over mass is equal to velocity divided by my magnetic field multiplied by the radius. So now let's go through my substitution. So my charge to mass ratio is equal to 3 times 10 to the 7 meters per second divided by 0.03 Teslas multiplied by 0.0057 meters. This is going to end up giving me 1.8 times 10 to the 11 coulombs per kilogram. So let's start thinking about what kind of particles these are. Well, if I look at this up here, originally we have nothing in here. So there was no charge at first. So it started with no charge and then it split into two different charged particles, a negative and a positive. Now we know the mass and we know the charge of an electron. So we know the charge of an electron is 1.6 times 10 to the negative 19 coulombs. We know the mass of an electron is 9.11 times 10 to the negative 31 kilograms. If I calculate this, I end up getting around 1.76 times 10 to the 11 coulombs per kilogram. Now this here is very similar to this here. So my answer is very similar to the charge to mass ratio of an electron. So remember, it's going to be hard to measure the exact radius of these particles in cloud and bubble chambers. Now, we look at this here, we have one positive and one negative. So that means we have a neutral particle that splits into a positive and negative particle with a charge to mass ratio of that of an electron. So in this case here, we end up with both a positron and an electron. So now here are two questions for you guys to try by yourself. These are the answers.